Have you ever just looked at a massive bridge or a skyscraper and wondered, how does that not fall down? It seriously looks like magic sometimes, but behind all of it is this hidden science. So today, we're going to crack open a classic textbook, Mechanics of Materials, to really get into the fundamental rules that hold our entire modern world together. Okay, so take a look at this bridge. It's beautiful, right? It's huge and it carries thousands of people. But how do the designers actually know, like with 100% certainty, that it won't collapse? I mean, what about a huge crowd or a massive gust of wind? Well, it's not guesswork, not at all. It's actually a science of certainty. And to answer that question, we gotta first understand a really cool concept. Every single object around us, from this massive bridge to the very chair you're sitting on, is caught in the middle of this invisible, non-stop battle. Yeah, you heard that right, a battle. On one side, you've got all the external forces. Engineers call them loads. That's things like gravity pulling down, wind pushing sideways, the weight of everything. And on the other side, you've got the material's own internal strength, fighting right back, resisting being torn apart or crushed. Mechanics of materials, at its core, is the science of predicting with incredible accuracy who wins that fight. So to make these super precise predictions, engineers need to get way more specific than just talking about a battle. And it all boils down to two absolutely key concepts that let them measure these forces: stress and strain. First up, we have stress. All right, imagine you're pulling on a rubber band. The stress isn't the force from your hands. No, it's the intensity of the force inside the rubber band itself, with all its little particles pulling back. It's the measure of how much of a fight that material is putting up internally. And what happens when that rubber band is under stress? Well, it stretches, right? That change in shape is strain. It's simply the measurement of how much the material deforms compared to its original size. Strain is the physical evidence of that internal battle we were talking about. Which, of course, leads us to the absolute million-dollar question for any engineer. Is there a consistent, reliable way to connect that internal pressure, the stress, to the physical stretching, the strain? Because if there is, then suddenly we can predict how just about any material is going to behave. And the answer, for a whole lot of materials like steel, is incredibly simple. It's this beautiful, powerful little rule called Hooke's law. It just says that stress is directly proportional to strain. And that E in the middle, that's the secret sauce. It's called the modulus of elasticity, and it's just a number that tells you exactly how stiff a material is. This one elegant formula is a cornerstone of all modern engineering. It's amazing. So once you have these concepts, stress, strain, and good old Hooke's law, engineers suddenly have this incredibly powerful and reliable toolkit they can use to design our world safely. Now, let's be honest. If you just flip through a textbook like this, you're going to see pages that look, well, pretty intimidating. Lots of symbols, lots of equations, but don't let that fool you. The actual logic engineers use is a really straightforward, repeatable process. It really just boils down to 4 key steps. First, you identify all the external forces pushing and pulling on your object. Second, you pick the right formula out of your toolkit. Maybe it's Hooke's law, maybe it's one for twisting or bending. Third, you plug in the numbers and calculate the internal stresses and strains. And finally, this is the most critical part. You check if those calculated stresses are safely below the material's known breaking point. And that's the whole point, isn't it? This isn't about crossing your fingers and hoping for the best. It's a rigorous process that takes these abstract ideas and turns them into solid, reliable numbers that tell you, yep, this is safe, or nope, back to the drawing board. For example, there's a problem in the book where they run through these exact steps for a redesigned engine shaft, and the final, concrete answer they get: the new design can safely handle a massive 890 horsepower. That's not an opinion, that's not a guess, it's a calculated fact. And look, these principles aren't just for some bridge in Nebraska or a high-performance engine. This stuff is the invisible foundation supporting pretty much every piece of our modern technological world. I mean, the scope is just huge. The book covers everything from the twisting forces in drive shafts, to analyzing the beams that hold up buildings, to the insane pressures inside a submarine hull or a pressure tank, and even designing columns so they don't buckle under weight. The same core ideas apply to all of it. And this is why this all matters so much. We step into an elevator, we get on an airplane, we drive across a bridge, and we do it with this unspoken trust. That trust isn't in luck. It's in the generations of engineers who have meticulously applied this math, day in and day out to make sure the things we rely on just work. So when we look back at that pedestrian bridge, we're not just seeing steel and concrete and cables anymore, are we? We're seeing a physical demonstration of Hooke's law. We're seeing a structure that was built not on hope, but on the quiet, powerful certainty of a calculation. It's not magic, it's mechanics. So I'll leave you with this final thought. The next time you lean against a balcony railing or walk into a skyscraper, just take a second to think about all those invisible forces at play and the elegant math that's guaranteeing they'll hold you up. What unseen calculations are keeping your world together right now?